Okay, let's talk about chapter 3, Fourier Transform. So Fourier Transform you should have learned in your 315 class. It's very important tool to help us understand signals or systems in time and frequency domain. So Fourier Transform is a pair of integrals, right? Transformation. The first equation is from time to frequency, and second is from frequency back to time. So we can relate time and frequency for energy signals or non-periodic signal. As we know, last chapter we talked about Fourier series for periodical signal. So this chapter we talk about non-periodical. So we cannot use Fourier series. The tool we're going to use is Fourier Transform. And for Fourier Transform, the transformation pair is unique. You have one x omega, you will find xt. Vice versa, if you have xt, you can also find x omega. Fourier transform. Next slide. Fourier transform is also a complex function, so it has a magnitude and also phase. Generally, Fourier transform magnitude will be even symmetric, and phase will be odd symmetric. So here is a next slide. We have an example for a given signal's Fourier transform. So here is a signal, right? A rectangular signal. This one's Fourier transform we know is sinc function. So next slide we show the magnitude or amplitude of the spectrum. We can find it's symmetric, right? Even symmetric. Okay, here we just want to review Fourier series, right? You have x0, x1, x2. You have f0, f1, f2, or a1, a2, b1, b2. So Fourier series give us discrete time spectrum. And for Fourier transform, the spectrum is continuous. Similar to Fourier series, we have the Basel theorem for energy signal. So the first part is in time domain. How can we calculate a given signal's energy? Right, we just integrate the whole entire signal's magnitude squared in time domain. And if we know Fourier transform of the signal, we can also do the similar thing. Integrate f omega in frequency domain, normalized by 2 pi. You can also get the energy for the given signal. Okay, then we're going to talk about some important Fourier transform pairs involving with impulse functions. Okay, the first one, impulse functions Fourier transform is constant 1. An impulse function with a time delay Fourier transform will be complex exponential e2 minus j omega t0. And those two pairs you can easily prove, right, by using the property of impulse function. Okay, next will be complex exponential. So complex exponentials Fourier transform will be impulse function in frequency domain. We have some other pairs like sinusoid, signum function, and unit step function. All those functions and their Fourier transform you can find from the table. So the table listed in the next 3 slides. Also in your textbook you can also find the Fourier transform.